Okay. So then I would put that in here, 50.5. And so those are our resultant vector magnitude and direction analytically. So this is called analytically or mathematically. Okay. All right. So that's what you would write here as well. And then let's see. So that's kind of this first portion. Then it wants you to look at it graphically again. So if I go back here, which is, I mean, we kind of did it earlier, but now it's wanting you to practice the tip to tail method. So if it says here, or the head to tail method, tip to tail, whichever, okay? So instead of having this resultant vector just given to us, I'm gonna get rid of it. Whoops, there we go. Okay. And remember that our head to tail method, we would drag this guy to that head. So we got this first vector plus our second vector we would put here, and then we'd bring in a third vector and go tip to tail. Okay. All right, so this would be graphically solving it. Just another way of looking at it. So our F is like our resultant vector that we just solved for. Okay, so we would write that down, what our magnitude and direction is. So right here, we have 15 as our magnitude, and our direction is 50 degrees. Okay, so now we have our graphically solved and analytically solved. Okay. And the main purpose of that is to compare our values. So then you'll go down here and you'll calculate your percentage error, which is here. So your experimental would be graphically, and your theoretical number would be analytically what we got. Okay, so you're just calculating the error of the magnitudes. Okay. All right. If you're not asking a question, I ask if you could please turn your mic off because I'm hearing background noise. It's distracting me. Okay. So this second part is similar, but now we will have 3 vectors. Okay.
Yeah.
Look at that. I can mute them myself. All right. So new information. Okay, so you're gonna do the same thing again, but now with 3 forces. Okay, so let's see. I'll kind of walk you guys through this, but hopefully it should be pretty much the same. Okay, so in this one, we're gonna say, okay, our first vector, I'm gonna just move these out of the way. First vector, vector D, we're gonna make it as 6 magnitude at 30 degrees. Okay, so that's our first one. Then we'll have our second vector, call that E. I'm gonna put that in the middle as well. It's gonna be a magnitude of 8, direction of 100. So let's see. Nope, not quite. Perfect. Okay. Then we'll have our third one at 145 degrees, right there, 11 magnitude. Okay, so let's see. So we're going to find our resultant vector by just clicking the sum. I don't know why it's way over there. We can move it, it doesn't matter. Okay. So this is our summation vector or our resultant vector. Okay, that's what it looks like with all those three forces or vectors. Okay. So we can put down our resultant magnitude as 18. I don't know why that happened. And our direction as 106.8 degrees. Okay. Now, this is where it kind of gets confusing again. This first portion gets really confusing. It says write down the value of FE and its direction. So I'm going to scroll back up and remind us of what that FE was. Okay. And if you notice here, okay, our FE was basically our, not balancing force, but our equilibrium force. So it's like counteracting that first or those other forces together. So if I want the force that's going to counteract this entire system here, I would just need something that's completely opposite to my resultant vector. So that's what it is asking for. And you can kind of see that here. My magnitudes were pretty much the same, right? They're about, 0.2 off, but they're pretty similar. And then if we look at our direction, it's exactly 180 degrees from each other. Okay. So that's what we're looking for. We're looking for something with the same magnitude, but the exact opposite direction. Okay, so then I'm just going to state that it's going to be the same magnitude and the complete opposite direction. So 106 minus 180 is what? Let's see. So 106.8 minus 180 degrees. Oops. That is going to give me a negative 73.2. Okay, and now let's look at the graph to make sure that makes sense. Okay, so if we're looking at this graph, we see our resultant vector here, right? If we want something exactly opposite, it's going to have to run somewhere this way, right? And a negative 73.2, that negative indicates that we're going clockwise from the x-axis. Okay, so this makes sense. Whoops. For my negative 72 to be completely opposite from that 106 degrees. Okay. Hopefully that made a little bit of sense. Of course, always stop me if I'm going too fast or just confusing the heck out of everybody.
Okay, that makes a lot more sense. Yeah, I see now where you're getting everything, and that makes more sense.
Yeah, I had a
I
feeling
appreciate
that this
it.
was going to be pretty confusing. So thanks for asking. Appreciate it.
Yep, and I have to go. I've got an appointment I have to be at, but thanks
No
for your
worries.
time.
Yeah, of course. Anytime.
I still don't understand it. I try to do this and I don't.
Okay. I think you came in a little bit later, so I can kind of go from the top a little bit. So
Yeah.
my first portion, let's see, my first portion was setting up these two vectors. Okay, so let's see. My first vector, I'm going to call that vector D.
Is this being recorded?
Yes, now it is.
Okay.
I think I started recording it a little late though.
Oh, all right. Because I came in late because
That's okay. Yeah, usually I will record them, but I just forgot in the first few minutes. So I can just quickly go back over this part really quick. So You want to set up your first two vectors accordingly. So I've got vector D, which is the first vector at a 20-degree angle and at 10 units magnitude. And then I have my second vector at 90 degrees and 8 newtons magnitude. Okay, so that's going to be my first setup. Then I want to, like I was just kind of mentioning, talk about my my force that is going to kind of balance it or counteract my summation here. So I'm going to pull this over here to kind of get it to make sense. So I'm going to take my third vector and try to counteract this summation here. That's what I'm doing. I'm trying to find my equilibrium, basically. So I'm going to make that summation as small as I can, which is probably about there. And so this will be my first vector here. Okay, so again, I'm just counteracting that other one. These two vectors that are adding together. So this is going to be my 15 newtons here, as you can see, and my direction as minus 130 degrees here. Okay, so that is the first portion. Then my resultant, which these really should be switched, those questions should be switched, but I can take that away and write down my resultant vector, which is here. Remember, the resultant is the addition of the two other vectors. Okay, so I'll just write down my magnitude and direction, boom, boom. And then, like I was just talking about, you can kind of compare what these two look like. Oops. Oh, there's a chat. Oh, perfect. Okay. Yeah, this is exactly what we're looking for. Okay. So we have the resultant vector and then something that would counterbalance that vector. Okay. So it's equal in magnitude, but completely opposite in direction. Okay. So then this next part is, I think what you came in at, maybe all this math stuff. That was when I was doing or solving this stuff analytically. So analytically just means like mathematically, basically. So I took my first two forces, which were given to me, their magnitude and their direction. And then I wrote down their X and Y components, and that is from here. So I can click on my first vector, vector D. My magnitude is 10. My direction was 20 degrees. My X component is here, D sub X. And then my Y component, D sub Y. So I fill all of that out, do the same thing with my other vector here. And then I can start solving for my resultant vector analytically or mathematically. Okay, and that's just taking my resultant vector, breaking it down into its X and Y components, and then adding those together, as you can see here. Okay. So that's all of this part. This next part where it asks you to do it graphically. It's kind of like what we just did here, but instead of having that summation vector on there, we do the tip to tail method and do something like this, where we've got the first vector plus the second vector, and then we can connect those using the tip to tail method. We get as close as we can. And then that would be our resultant vector. So they're just showing you different ways of how to work with vectors, add them together mathematically and graphically. Okay. So hopefully that helps. And then part 2 is pretty much the same thing, like we just talked about. And then there's a few questions at the end that you can answer. And that's pretty much it for the lab. It sounds a lot more confusing than it actually is. And that's why it took me a little bit in the beginning of the this recitation to remember how we did it, or how I did it on my own time, because I was a little confused too. Okay. Okay, and you did ask about homework. Oh, good. I know this takes a minute to understand, so don't feel bad. Let's see. On questions 5 through 7. Okay, so let me go to the lab. Okay, let's see. How can I do this? I'm gonna put you guys to the side and then get this smaller. Okay. I see it where I can read it at the same time. Okay, so question 5. I'm gonna scroll down here. No. Okay, there we go. So question 5. No. Sorry, I'm still learning this stuff too, okay? It's kind of difficult online. All right, so number 5 says that we have a golfer who hits a ball from the horizontal ground and gives it some initial velocity. So I'm gonna write these things down as we go. So initial velocity of 35 meters per second at some angle of 28 degrees, okay? Oops. What does the chat say? No worries. Okay. So we have golfer who hits it at 35 meters per second at an angle of 28 degrees, okay? And we want to first know where the ball will be at time equals 2.4 seconds after it's hit. Okay, so where will the ball be? So the Y and X probably components of where it's going to be. Okay, so I'm going to extend this and then get this out. So we're going to be using these equations a lot. So I'm going to keep them out here. Okay. So we have some velocity, some initial velocity. And let me actually draw this out for you guys, because I think drawing these things is helpful. So we've got a ball that's going to be hit at some angle with some velocity. And we want to know at some time, where is that ball going to be? Okay, so say that this is the time. Where is that ball going to be? Okay, and remember that this is our X and our Y directions. Okay, so just to kind of give you guys a visual, this is what we're looking at. All right, so what I start doing is I start looking at these equations and say, okay, which one fits what I have, what I know, and what I need. Okay, so let's see. I have my velocity. So I have my V naught, which can be put into V naught X or V naught Y. I have my initial angle. Okay, and then I have some time. Okay, so I have my time. All right, so I'm gonna start looking at my horizontal motion and see if I can figure something out here. Okay, so I'm going to just state that where my ball was initially hit, okay, where that ball was initially hit is going to be X naught equals 0 and Y naught equals 0 meters. So I'm claiming this because I don't have any kind of like height information. So I'm just gonna say, okay, this is my origin now, okay? Now what I will do is I'm gonna look at my horizontal motion and I'm gonna get this first equation here. X equals X naught plus Vx t, okay? So I have my t, good. My Vx, if you notice here, and hopefully you guys remember from lecture, is that the velocity is constant in the x direction. So I have this number because I have my V naught value. I have my x naught that was just given, right? I just defined that. So now I can solve for my x. So I'm gonna start plugging things in. So my x equals 0 meters, which is the first thing, plus, now that can be my V naught x, okay? So V naught, 35 meters per second. And remember to get your x direction, it's going to be the cosine of the initial angle here. So that's what I'm plugging in right now. I know this is kind of crammed. Let's see. So cosine of my angle, which is 28 degrees. And then multiplied by my time, which is going to be 2.4 seconds. Okay, so then you'll plug everything in, you'll find value, and so now we have our x. Okay, so we'll do the same thing for our y, but now we got to find another equation. Okay, so let's look here. So we have our y naught, we have this value, which is in these two equations. We have our Vy naught, but we don't have Vy. We don't know, whoops, we don't know what our velocity is at that time. So we can't use that equation, but we do have G, or gravity. So I'm gonna use this equation here, 3.39, okay? So again, remember in all of these trajectory motions, or projectile motions, sorry, we always have G involved, okay? So we always know that number. So now I'm going to say Y equals Y naught plus V naught Y times T minus 1/2 GT squared. Okay, and this is 0, if you remember, 0 meters. My V naught Y is going to be V naught times sine of theta naught. Okay, so I can plug all of these values in and solve for my Y. Okay, so I have a T, I have my G, I have my T, now I have that number. So plug it all in and you've got your Y component. So now you know exactly where that golf ball is at some X, comma Y, if you want to think of them as coordinates. Well, it really is coordinates. Okay. So that's for part A. And a lot of these are going to be kind of repetitive, just in the way that they're formed, but you just got to remember, you know, how to kind of set everything up and make sure you're looking at your equations, going back and forth. Okay, so the next one, or the next question, B, is asking what will be the greatest height reached by the ball. Oops. So greatest height. Okay. So what I did when I was solving these problems is completely just using these equations. But I also noticed that in your textbook, if you scroll down, you keep scrolling to about somewhere right here, it actually tells you how to calculate your maximum height just from one little formula. So we can also use this instead of having to kind of use more algebra, I guess, to make an equation like this. I can just say, hey, here's the height, boom, done. So that's what I'm gonna do for you guys right now. So I'm gonna use this equation here, my height, oops, I don't know what happened there. Now it doesn't want to erase. Well, that's bizarre. Okay, well, just ignore that. My greatest height, h, is going to be equal to v naught y squared divided by 2 times g. Okay, and that's it. So I'm just going to plug in my values. So again, I have my v naught y here, so I'm going to say v naught times sine theta naught, that whole thing squared, divided by my 2 times g. And that's it. That's all you got to do to find your greatest height. Okay? One thing to note, remember that g is 9.80 meters per second squared. Whoops, glitch in the computer system. Oh no. Okay, well, we'll deal with that in a second. Okay, so this is part B, finding the greatest height. Boom, right there. Just that equation. Okay. Now let's see for part C. Whoops. Where will the ball land? Okay. Now it's asking where the ball will land at the very end of its trajectory. Okay, so at the very end, why is this doing this? Oh no. Sorry, my computer is not being nice. There it goes. Okay. So again, where will the ball land? Where is it going to be at the very end of the trajectory? Okay. Will it land? So again, I was trying to use some fancy algebra to solve this, but it's actually an equation in your book as well. So I'm going to scroll down. And they refer to it as its range of the projectile. So the range of the projectile is really just where whatever the object is going to land at the end of the projectile. So I'm going to, whoops, use this formula here to solve it. So my r equals my v naught squared times sine of 2 theta naught. And when it says sine 2 theta naught, it's like in a parenthesis here. Okay, be careful with that. Divided by g. Okay, so all you do is you plug in your values. So my v naught that was given to me is 35 meters per second. Right, so 35 meters per second. So that is squared times sine of 2 times my theta naught, which was 28 degrees. Divide that by my g, 9.8 meters per second squared. Okay. And then that's how you get your range. So this is range also the final position of the whatever the object is, the ball, the whatever it is, the rock, okay, of a projectile motion, okay? All right, so that is for number 5. Let's see. Okay, no problem. So I can continue with number 6 now. Let's see. Number 6, we have a rock that's thrown at some angle. Whoops. Okay, so let me scroll down here. There we go. I don't usually write this horribly, so sorry, bear with me. Okay, so a rock is thrown at an angle, 45 degrees. It does not like me right now. Well, that's interesting. Okay, 45 degrees. Let's see. At a height, so I'm gonna call that Y naught, of 1.8 meters from the ground. The rock reaches its maximum height. So I'm gonna call that like T max, just so that we know that it's a maximum height at 2.0 seconds. Yeah, we can continue and keep going, working on them until we're out of time. So hopefully, if we have time, I can go through 8 too. So let's see. So for number 6, we have a maximum height at t equals 2 seconds. After the release, we have a starting position. We want to know the initial velocity of that rock. Okay. All right. So, okay. So let's see. It doesn't want to draw now. Okay. So let me draw this because it's always better to have a visual. I'm having a hard time here. So we are at some height of 1.8 meters. Okay. And this thing is thrown. Okay. And we want to know, what are we asking? The initial velocity of the rock. So we're saying at my maximum height here, we know that it takes 2 seconds to get there, okay? And we want to know the initial velocity based on all of this information. Okay, so let's see. Thinking about my maximum height here, we remember that at my maximum height, my velocity in the x direction stays the same throughout my trajectory, right? Remember that. We also know that my velocity in the y direction at maximum is 0. Okay, that's given because that's in like free fall. When we throw something up, it stops, turns around, and comes right back down. Okay, so this is kind of what we're looking at like here. Okay, so we need to know this information in order to solve the problem. All right, so let's go back up to our equations and see what we can do. Okay. So we have our time at the maximum. We have our velocity at the maximum, but we don't have our velocity in the x direction, just our y direction. Yes, it will be. Okay. So let's see, we have our V max, our V Y max. We have our Y naught. We don't have a Y. We have this guy. Excuse me. Okay, so that's what we will need to use, I believe. So we have our V naught Y, which is going to be 0. Okay. We want to know our V naught Y, so our initial velocity in our Y direction. We have G and we have T. So let's go ahead and use this equation here. So Vy equals V naught Y minus GT. Excuse me. Okay. And so this is 0. Okay, because we're looking at our maximum. Our T we have here as 2.0, and we know our G. Okay, so using that, I can find my V naught Y at least equals G times T. So 9.8 meters per second squared times 2. And that gives me what? Do, do, do. 19.6 meters per second. Okay. All right. So I have that. Now, again, I'm wanting to know the overall velocity, not just my y component of the initial velocity. So what I'm going to do is a little trick, okay? Remember that my V naught y is V naught times sine of theta naught. Whoops. Okay. So what I'm going to do now is I'm going to solve for my, initial velocity here. Sorry, I'm not very good with the pen yet. I keep clicking buttons. Okay, so I'm going to solve for my V naught here by plugging in these numbers. Okay, so my V naught is going to equal 19.6 meters per second. I'm going to divide that by my sine of theta naught, which is 45 degrees. Okay, so then my initial velocity now is going to be 7.7 meters per second. Okay, so that is my initial velocity of that rock. Okay, now part B is asking for that maximum height. And that's the same thing that we used earlier for the above problem. So I'm just gonna say, okay, see this equation, that's what you'll use again. So my maximum height, H, is gonna equal V naught Y, whoa, V naught Y, there we go, squared, and then divided by 2 times G. Okay, so that's what you use to find your maximum height of that trajectory. So then that should be good. Okay. Now my final question, what is the velocity at the maximum height? Okay, so let's see. When we were analyzing our little sketch here, we know that our velocity in the y direction at maximum is 0 meters per second. Okay, but we didn't know our v sub x. at maximum, which is also the entire, our velocity in the x direction the entire time, right? Because that doesn't change. So we basically just need to find that value then. We need to find v sub x or v sub not x, okay? So we need to find this value, okay? And this should be easy enough because we know that our v naught x is just v naught times cosine theta naught, okay? And so we have this value from up here, from part A, and we have our theta naught from the problem given. So it's going to be 27.7 meters per second, okay, times cosine of 45 degrees. Okay, and so then we just get 19.6 meters per second, I believe. Let me double check. 7. Yes. Okay. So what this really means is that our velocity at our maximum height, okay, or our velocity, our velocity at maximum height is going to be calculated from a couple of things. Remember that our velocity is calculated, or a magnitude, magnitude of a vector is calculated in this way, where we have the two components, square them, add them up, and then take the whole square root, okay? So I need to do the exact same thing to find my velocity. Okay, so my velocity at my maximum is going to be that 19.6 plus my velocity at maximum of the y component, which is just 0, meaning that it's just going to be 19.6. But I wanted to show you guys how you would do this theoretically. Okay, it's not always going to be 0 in the y, but when it is at maximum, of course, yes, it is. Okay, so our v max is going to be our Vx. Okay, so just remember that. But you can always just plug your numbers in just to be safe. Okay, if you forget that, just remember how to solve for magnitude of a vector. Okay? Okay, so I know that was pretty quick, but like someone asked, I will put these on Canvas when we do recitation time, so don't worry about missing something. It should be up there too, okay? All right, so I'm gonna move on then, if there's no questions, to number 7. So we have a basketball player running at some velocity towards the basket. Okay, so we have, I'm gonna draw it right here. Basketball player running in this direction, it's just horizontal. Okay, our V naught is 4.5 meters per second. Okay, and my first question is, what vertical velocity does he need? Oh, good, I'm glad. That's why recitation is so important. It is meant to be helpful. I remember we never had anything like this when I was an undergraduate. Until my senior year, we had something like this, and I was like, why haven't we been having this the entire time? So anyway, a little off topic. Okay, so for number 7, part A, what vertical velocity does he need to rise 0.73 meters above the floor? Okay, so this one is a little bit funny, okay, when we think about it. But we have some initial velocity going this way, and we want to see what he needs to do, or what velocity he needs to get up to some height, 0.73 meters. Uh-oh. Okay. So I'm gonna take this and move it. All right. So I'm gonna start looking at my equations. Okay. Whoops, not that button. Here we go. And look at what I have. So I'm gonna say that my x naught and my y naught are equal because they're gonna be equal to 0. Okay, I'm gonna claim that is my starting position. And I need to go up to some height of this. So I'm gonna say my y final is gonna be 0.730. Okay, so let me look at my equations here. What do I have? What can I solve for? All that good stuff. So I'm gonna look at the vertical stuff because I'm trying to move in that vertical direction. Okay, my velocity here is only horizontal. So I can just state that my velocity in the y direction is just 0 because it's only horizontal. So this could also be my v naught x, okay? So let's see. I'm asking what velocity do I need, right? Yeah, what vertical velocity do I need? So I'm gonna go here and say, well, here's the velocity here. I don't have any time though, so that doesn't help. This actually has a height difference, which is what I'm looking for, right? So let's try to use this equation, okay? So I've got some Vy that I'm solving for, and my V naught y, 2g y minus y naught. Okay, so let's see. So this is gonna be kind of funny. The way they worded it, I think, let's see. There's no to do. Sorry, I'm thinking. Give me a second here. Vy. Well, all right. So my velocity, is it asking for maximum or no? No. All right. Ooh. Okay. So this value is going to be 0 meters per second. That was kind of given since he was running horizontally, not vertically. And then my y minus y naught is going to be 0.730 meters. Okay, this is my y value. Okay, so let's see. If I plug these numbers in, okay, bear with me for a second. This might get a little bit confusing. If I plug these numbers in, this is what it is going to look like. 0.730. Okay, and as you can see that there is this negative out here, which doesn't make sense. I can't find out how to get that away other than switching these two, which doesn't make sense to me. But our values should be fine if we just ignore the negative, which I know sounds terrible. But see, if I take a square root of this, which is what I'm gonna have to do, I would get a negative under a square root, which doesn't make sense. So bear with me just for the sake of this homework problem. Ignore this negative. It will be the same magnitude. Okay, so just ignore that negative. Yeah, the only way I can think of is switching those two. It doesn't make sense to my brain. All right, so my velocity then, is going to be the square root of this number, which is, let's see, 2 times 9.8 is 0.73. Square root of 14.3, which is what? 3.78 meters per second. Okay. So again, for the sake of this problem, this is what you're going for. I'm not sure why there's this negative then. Okay, so just bear with me there. But in any case, I can just say our magnitude of this number is the same. Okay. So our velocity in the y direction is 3.78 meters per second. Okay. All right. Okay. So our next question is, how far from the basket must he start his jump to reach his maximum height at the same time as he reaches the basket? Okay. So we're gonna have to do a little bit of thinking here. So, come on, pen. Horizontal direction, must he start his jump to reach the maximum height? So our max height, remember, is going to be where our velocity in our y direction is 0. Okay. Let's see. So this guy's going to equal 0. So we want to know what x would have to be. If you guys have any suggestions, let me know. I'm thinking of it. All right, so we still don't have our initial velocity, do we? Wait a minute, we would have our initial velocity because this velocity at the time of our projectile, right, that would be our initial velocity in the y direction, right? Yeah. Okay, so we've got this guy running this way, right? And then he starts his jump. We don't know anything about the angle, but our x velocity, our x component of the velocity remains the same. And then we add some kind of y velocity, which is this, right? So our vy, or vy naught, v naught y, just add it like that, is that 3.78 meters per second. And then my v naught x is that value that we were initially given. So that 4.5 meters per second. Okay. So as you can see, it kind of takes a little bit of thinking to get to these ideas of how to move along. Okay, so bear with me. Okay. So now we know a little bit about our initial velocity. Okay. And we want to know at what x, or what should our x not be, such that we get our maximum height to be at the same as the ball, or same as the hoop. Where is the hoop? Is the hoop at the same height that was given to us? It doesn't say. Maybe it is. I would assume so. I would assume that we would want that maximum height to be that height that was given to us, this guy here. That's what I'm gonna assume. Okay, so let's say my y at max. Wait a minute, let's see. Oh, but we don't have our theta. But we could solve for theta. This is taking quite a bit of thinking here. Oh, we do have that. Okay, so let's say our y max is going to be this formula here. Okay, so let's plug our stuff in. 3.78 meters per second. Square that. Divided by 2 times 9.8 meters per second squared. Boop. And so that is, oh, sorry, twisted my wrist, which is not what I'm supposed to be doing right now. Okay, so 8 divided by 2 times 9.8. It is. Cool, cool, cool. Okay, so this is 0.729, which is pretty much the same as what we were given. So that 0.73 meters. Okay, so we're going to use that as our maximum. So at what distance? So let's see. Looking at my equations here. What time? We need a time. We need a time when we hit that maximum. So let's see. Yeah, we need that time. If we have that time, we can solve the problem. So we have our y naught. We have a y, which is our maximum, we're going to say. We have a v naught y, and we have a g. So let's use this equation here. Okay, so y equals y naught plus v naught y times t minus 1/2 gt squared. Okay, our y is going to be our y max. So I'm going to plug in our original number, which is y equals 0.73 meters. Okay, so I'm going to say we have that number. Our y naught is 0 meters because I claimed that in the beginning. Our v naught y we have up here. Okay, and then we're solving for time. So let me plug in my numbers. I have 0.73 meters equals v naught y, which is 3.78 meters per second. We have some time that we don't know, minus 1/2 9.8 meters per second squared times t squared. Okay. So as you may notice, we now have a quadratic formula, or yeah. So we're gonna need to use, or not the quadratic formula, we have an equation, right, that has quadratics in it. So we're gonna have to solve it using that quadratic formula. Okay, so let me go ahead and move some stuff around just to make it more pleasing to the eye, I guess. So I'm going to say 1/2 times 9.8 meters per second squared times t squared minus 3.78 meters per second times t plus 0.73 meters equals 0. Okay. So I put everything onto one side and now I can solve it. Okay. So we're going to compare this to our ax squared plus bx squared. Oh, I'm sorry. Plus bx plus c equals 0. And remember how to solve this is going x equals negative b plus or minus the square root, b squared minus 4ac all over 2 times a. Okay, so this is what you're comparing it to. So I'm going to go ahead and plug everything in like I have here and solve for my time. Okay, so equals negative, my b is here, which is negative 3.78. Okay, plus or minus square root of that number squared. So I'm going to ignore the negative, well, I'll put the negative in there. Squared. Okay, minus 4 times a, which is 1/2 times 9.8 meters per second squared times c, which is 0.73 meters. Okay, so this is all under square root. Then we divide that by 2 times 1/2 times 9.8 meters per second squared. Okay. All right. So then what you do is start solving. So these two negatives cross out and they're a positive. My negative here is squared, so that's a positive now. And then we are pretty much good. I can simplify a little bit more. Let's see. Let me get another color out. Maybe that'll help. This 1/2 can make that 4 into just a 2. This 2 and 1/2 cancel, okay? So I'm gonna go ahead and write down here what I have so far, 3.78 meters per second, plus or minus. And then I'm gonna square this here, so 3.78 squared is 14.29 meters squared per second squared, minus multiplying all that out, 2 times 9.8 times 0.73. I get 14 point, ooh, is that right? That does not look good. There's something wrong here. That can't be right. Let me see here. Maybe I made a mistake somewhere. It's a positive. I put that over. It's a negative. I put that over. It's positive. This seems off. So the reason I stopped here was I saw that if I were to subtract this number from this number, that there's going to be a negative value under there. Also, it's interesting that their numbers are so close together. Let's see. Seven. Is anyone seeing a mistake? If not, that's okay. I don't know what is going on here. Maybe I should have used this 729. That is the only thing that I am seeing. That would have been different. Let's see. So if I plug it in there, there, and then here, let's see, 0.729 meters instead. That would give me 14. These numbers are just so close. If I were to round off, oh boy, then that's 0. Is that okay? Probably. Let's see. The negative 1/2. Up here. So what I did here is I plugged in my negative 1/2, of course, and then my 9.8 here, meters per second squared. And then I moved everything over to one side. So I added this over. So then it would be a positive, which is what I have here. And then, so if I added that over, subtract this one over, and this would be, yeah, that should be fine. And even if I didn't do that, then this value would have been negative. If I had that on this side, that would have been negative. And then I'd have a negative times a negative times a negative, which would be negative. That's just odd. I don't know, maybe this is all fine, but it just seems very odd to me. So I guess we'll continue. Let's see what we get here. So if that is 0, then I'm just getting 3.78 meters per second over 9.8 meters per second squared. Let's see what that is. So 3.78, 9.8, 0.38 seconds? Actually 3.9. That doesn't seem like very much time. Let's see. I can't think of anything that would be different.
Just skip it, go to the next one, so then a video of what it is when you have time, I think. That's what I would do.
Maybe I should do that. So as of now, I'm not finding any kind of mistakes or anything. So
Freebie.
yeah, I might have to give this one to you guys, and then I'll solve it on my own time. For some reason, it's just not coming to me why it would be any different. But I am not convinced that this is the time, since it's such a short amount of time. So yeah, what I will do is I will solve it on my own time and then post a video of it. And of course, that won't be on the test if it's this difficult and it takes this much time. Okay. So yeah, let me just move on ahead. I know that there was someone who wanted to talk about number 8. Okay, so I am going to, again, I will look at this on my own time, find some kind of mistake if I can, or maybe using the wrong equation, which I don't see how, I'm not sure. So I'm gonna have to look at it on my own time, okay? So just bear with me and I will probably post that a little later today, okay? All right, so let me look at number 8. Okay, so number 8, I didn't really talk about it much in the lecture, so this would be a good time to kind of go over it. Okay, so we are looking at, excuse me, these velocities here of galaxies, okay? And we want to know about relative velocities. Okay, so I've got a couple examples here of what it means to have a relative velocity or think about them. So we know, for example, we live on Earth, right? Pretty sure most of us do, or all of us do. And the Earth is moving at some crazy speed, right? I've got it here as 67,000 miles per hour. Okay, so the Earth is moving really fast, okay? But as we're sitting here on Earth, okay, on our little Zoom meeting, we don't feel that speed, right? We're not feeling that velocity. We just feel like we're just sitting here and we're going 0 miles per hour, right? It doesn't feel like we're moving. But that's what a relative velocity is. So relative to the Earth, we aren't moving, okay? But relative to the sun, we are moving, okay? And we're moving at some velocity, okay? Another example is if you're driving in a car, okay, and you're going, say, 50 miles an hour down the freeway, okay, and another car passes you, so you're going 50, they're passing you, and it seems like they're passing you really fast, right? So maybe like 20, maybe they're passing you at like 70 miles per hour, and you're like, whoa, dude, like it's a 50 through here, right? So if you're going down the freeway going 50 and somebody passes you at 70, okay, your relative velocity would be the difference in your velocity. So his relative velocity to you is going to be 20 miles per hour, if that makes sense. So they're going 20 miles per hour faster than you, right? So it's like when you're in a car, you feel like you're not really moving, right? Because relative to the car, you're not moving until you like look out and you see the trees flying by, right? Then you're like, okay, I am moving. We are going 50 miles an hour, whatever. Okay, so that's what relative velocity really means, okay? So when we're looking at these galaxies here, that's what we want to know. So if I'm looking at our Milky Way galaxy, which is galaxy number 3 here, and I want to know the relative velocity of galaxy 4 to us, okay, our relative velocity is going to be 2,830 kilometers per second. Okay, so that is the relative velocity of galaxy 4 to the Milky Way, or to us. Okay. So let's see. My first question that says, calculate the velocities relative to galaxy 3. I guess it's not really calculating, but what is our velocity relative to the Milky Way? But we're in the Milky Way. So it seems as though we are not moving. So then it would just be 0 kilometers per second. Okay. That would be the first one. The next one, relative to galaxy 2. So what is the velocity of, what is the velocity relative to galaxy 2? So since galaxy 2 is moving away from us, okay, it's as if we are moving backwards in a sense, because they're moving away from us. So that's why we have the negative here. Whoops, that's why there's the negative here. It's just direction, remember? And then it would be the 2,200 kilometers per second. I believe that's all it's asking for. I mean, I wrote it, but it's been like a few days or a week. Yeah, and then the last one, relative to galaxy 4, same idea. How fast is that galaxy moving relative to us? Okay. So that's pretty much it for number 8. That's all it really is asking. I just wanted to get you guys to understand kind of that idea of relative velocity. Okay, but that's basically it. Okay. All right, so does anybody have any more questions other than that one that I am stuck on right now that I'll have to take some time to think? You can either type it or unmute yourself. I did go over lab earlier, and I will put this on Canvas, so if you missed it, that's fine. You can watch it over. Number 6, I did do. Yes, I did do that one. That one, let's see. I did that one right before 7, and that one's not too bad. It just takes quite a bit of thinking and a lot of math, but it'll be posted as well. Just seeing if there's any more questions. All right, if there's no more questions for now, you can feel free to continue the homework, and then if something pops up, just let me know. I'll be on here until about 3 o'clock, okay? So you can either use the chat or just unmute yourself, whichever works for you. I'll be working on number 7. We are solving for that one. Yeah. Number 7 needs more information.
I have that on some of mine. Okay,
Mm-hmm. Mm-hmm. Number 4. Did we do number 4 together? Let's see.
No, we didn't do number 4. I was just saying because I did it, and I don't know. I got a negative like 8 point something, and I'm confused.
Okay. Let's see. Maximum height reached by the arrow. That would seem odd to get negative. Let me see if I did that one.
I'm trying so hard. I'm reading the book, watching YouTube videos. I'm so like,
Yeah, it is hard. I understand, especially doing online. It's not helping.
if I was in class, I'd just be asking questions 24/7. That's just who.
And that's fine. Yeah, I understand. It is rough to do, especially any kind of math or science. It's really hard online. It really is.
Yeah, I took calculus online, and it was rough, but I still passed.
Oh.
It was hard.
God,
no.
that's rough.
And I'm not. And now I'm taking organic chemistry and biology and this one, so I'm drowning.
Yeah, I bet. Oh my gosh. Crazy. Let me see.
For me, for me, it's basically similar but I have to take calculus as well along with this class right now. So, yeah.
Yeah, I took it. I took the summer calculus class, so it's accelerated, and we did it in 5 weeks.
Holy
Damn.
cow. Dang.
I passed an A. All right. I didn't sleep, but I did it.
Well, that's good. But not that you didn't sleep. That sucks.
I don't even know what that is anymore.
Valid. What is sleep? Oh, look, I did number 7 before. Shoot. Okay, but where is number 4? I had to have done that one.
You're gonna look at my homework, and you're like, at least she attempted.
Pretty much. I feel like that's kind of how it's going to go for the semester. That's the hard part. Let me see. Number 4. As long as it's not like, oh, here's an answer and no work, that's what I hate. But if there's work and I can see that you tried, that's good. That's better than getting the right answer to me. Okay. So let's see, number 4. Why?
So we're doing number 4.
Yeah, let's go ahead and look at number 4 because I can't find my answers for it. So we've got, I know I started it. What is the height of the cliff? I found that.
Are
What
you
if-
gonna upload the OneNote sheet or just the video?
I was just going to upload the video. I don't plan on uploading the OneNote sheets. Or do you
All
think,
right.
I don't know.
Yeah, I like examples to keep my like I print them out and I put them in my.
Oh, that's a good idea.
I'm an example person. I need like any
Okay.
examples, all the above.
Yep. That's why I'm trying to do as many as I can with my lectures. But
I watched all those and I was like, yeah, I'm trying.
yeah, it's hard. I understand. Try to do as many as I can. Can't get all of them in though.
Yeah.
So maximum height, that is going to be where our velocity, oh my goodness. Come on, OneNote. The hardest time. Velocity in our y direction would be 0 at that point. We have our initial, come on, OneNote. Our initial velocity, 32 meters per second. This guy here is 66 degrees. Maximum height. Oh, we can use this fancy equation down here that I just learned about. So our maximum height, we can use this equation. So that's what I'll do. H equals V naught Y squared over 2 times G. So my V naught Y is going to be V naught times sine theta naught. So that's how I would solve this one. So let's plug in our numbers here and see what we get. $9.8. Okay. So 32 sine of 66. Square that. Come on. Divided by 2 times 9.8. I'm actually getting a 43.6 as my maximum height. Whoops. Oh, but you know what? Let's see. That is going to be my maximum height. So, okay, so for this problem, let me just explain something real fast about this problem. It also asks you, or it tells you, sorry, that the starting height is 1.5 meters above the ground. So what we have is an arrow shot like here above the ground. And so when we're looking at the trajectory, okay, now I'm just drawing all over. Sorry, I'm getting messy. Let me scroll down. So when I'm looking at the trajectory, okay, I'm just looking at it from that height. And so I have to make sure that I add that height in as well. So my maximum height here, this value is just from here to there. So I have to add this extra 1.5 meters to it. So just watch out for that. So my entire maximum height would be that 43.6 plus 1.5. So whatever that is, 1 and then a 4, 5, 4, something like that. If I did that correctly in my head, I can't do addition anymore. It's gone. Hopefully that's right. So just watch out for that. I think what happens is that our brains kind of think that this stuff is so hard, and then we forget like to just kind of simplify it, because I know that that's what I do, and that's probably what I did for number 7, why I can't solve it right now. So watch out for that. Don't overthink things. I tend to do that a lot. So that would be my whole maximum height for that trajectory. Okay, and that's from the ground. And then it asks for the impact speed. So that's going to be like our final speed of the, what is this, an arrow? Before hitting the cliff. That's right, so it hits some cliff here. And it stops. Say there, I'm not really sure. And that's at time t equals 3.5 seconds. So we want to know the impact speed. So we want to know the speed, oops, there. If we find those two, we can solve for the total speed. Let's see, or the speed vector. Do I need anything from here? I don't think so. Let's see here. Did I ever solve for? So I know that, remember in the trajectories, I can say it, the velocity in the x direction remains the same throughout, okay? So my Vx is gonna be the same as V naught x, okay? So I'm gonna say it equals V naught times cosine of theta naught, which is what, it was 32 meters per second times cosine of 66 degrees. So now I have that number. And then I need to know my Vy. So I know my V naught y, that's given, or I can solve for it, not that it's given. I know my final position, y. I know t. I know y naught, that's 1.5. So what equation do I need to use? Let's see. So I need this one. I know the time, yeah, because the time is the time of impact, I believe, is what the problem says. It lands on the top of the cliff, yeah, 3.5 seconds. So I can actually use this equation here, this one that says Vy equals V naught y minus g times t. I can use that equation. So we've got 32 meters per second minus 9.8 meters per, oh, whoops. Whoa, hold on, back it up. 32 meters per second, but we need the y component, so that's gonna be sine of 66. That would have been a big boo-boo. See what happens when you try to go too fast through these things. Okay, and then our g times our time, which was 3.5, right? Yeah, 3.5. 3.5 seconds. And then we can solve for that one. So I'm gonna go ahead and do these real quick just to kind of get our minds on it. So cosine 66. This one I'm gonna write it right here. V naught x or Vx equals 13.0. And then this one, sine minus 1.8 times 3.5. That's actually a negative 5.07. Remember that the negative is giving us direction. Okay, so the fact that it's negative is that it's no longer going in the positive y direction, it's now coming down in the negative y direction. So like my little sketch here, this would be all positive y, and then when it starts to, after that maximum, it's going to be negative, okay? Okay, so if I want to know my total speed, or yeah, total velocity, I will use vector addition. Okay, so you plug these guys in, 13.0. Oops, that's not a squared there. Plus negative 5.07 square root. Oh, not pretty, but it works. All right, so that squared plus 13 squared square root. So my velocity then is, or my overall total velocity when it hits is actually 14.0 meters per second. So that's how fast that arrow is going when it hits the cliff. Okay. Ooh. So hopefully that made sense. Yeah. That other question. Time is it? Okay. Did I overthink that one? Most likely. So I guess I did. Oh, that hurt. I touched my wound. That was good. It's okay. It's over the bandage. It's fine, right? I'll be fine. Okay, so apparently I did do number 7 before. So, and I really did complicate it a lot. So I can go back right now if you guys don't mind me to do that. And I'm going to be going off my notes because it's been a minute since I did it. Obviously, I forgot completely. Okay, so I'm going to go back up there and restart. I actually got the right time, but I made it way too complicated, let me tell you. It is only like a half a page on my notebook, but I made it nice and complicated for you guys. So I'm gonna backtrack, okay, and kind of restart number 7. Okay, so bear with me, all right? So we're just gonna kind of ignore all of this and let me go ahead and start this again. So I know where the negative came in and all of that, so I'm gonna just go over here and do it over here. Okay, let me try to get over here more. Okay, so number 7, redo. Okay, so number 7 said, what did that one say? Oh, it was the basketball player one, right? So we had that, our velocity in our x direction was, what was it, 4.5? Right? And that it was purely in the x direction, so we can just write down that our y is 0, just so that we know, okay? And we are trying to see what our velocity is, or what our vertical velocity needs to be to get this height, this 0.73 height. Okay, so we want to know what we need to make our initial velocity. What should this be in order to get our height? Oop, stop it. I'm struggling, you guys, with my computer right now. Okay, and my mom is in the corner laughing at me. I'm in her office because I don't have a great office yet. I'm in an apartment, so this is better. All right, so my height is going to be this guy here. The 0.73, right? Yeah, 73. I can read. Okay. So let's start this again. We are going to be using that equation that I wrote down over here. So that Vy squared equals V naught Y squared minus 2Gy minus Y naught. Okay. But this time I'm going to define things a little bit differently. Okay. So as you can see, I'm looking for a V naught Y, not Vy. Okay. So see how last time I defined it differently? Yeah, we're not going to do that. Okay. So we want to know what our initial velocity in the Y direction needs to be. So I guess we don't really know that it is 0 to start with. Okay. So we need to know what velocity we need to put on this guy, or what velocity this guy needs to do in order to get this high in the air to jump. Okay. And it doesn't state it in the problem, but this is going to be our maximum height. Okay. So at our max height, we know that our velocity in the Y direction is 0, right? So this is at our max height. So 0 then is going to be equal to our V naught Y squared minus 2Gy minus Y naught. Okay. And I'm going to go ahead and define that my Y naught equals 0. And my Y I can plug in here. Okay, and then I can solve for my V naught Y. So V naught Y squared equals 2G times Y. Okay, so I added this guy over so it's both positive, which is better than what we had last time. Okay. 3 meters. Take the square root and we can get our V naught Y is what? So 2 times 9.8 times 0.73. Square root, whoops, 3.78. Now again, as you notice, it's the same exact answer we had last time, but I was like, hey, doing hand waving things, saying ignore the negative, blah, blah, blah. It's just because that we defined things incorrectly from the beginning. So it's really important to take your time and really understand the problem, and that's what I was not doing. I was trying to rush these things, okay? So this is for part A. So it's pretty similar, just tiny difference. Now part B, this is where we are looking for the maximum height. We're saying at the maximum height, we want that to be the same time as he reaches the basket. Okay, and we want to know how far from that basket he needs to be. Okay, so I overdid this one as well. So we're looking at what distance we need to be at. Okay, so say we're looking at this little thing here. There's the hoop. Okay, what distance does he need to start his jump? is basically what we're looking for. So that this is where the maximum is. I'm sorry, not Vmax, but the maximum height. Okay, so I'm gonna go over here and look at my equations again. So we have my V naught Y, and we have, let's see what else. We have Vy, which is gonna be 0 at our maximum height, right? Our Vy is gonna be 0 here. So I'm gonna use this equation to solve for time. Okay, so I have Vy equals V naught Y minus G times T. And so I need to know what time that will be at. Because if I know that time at which I will have that maximum height, then I can go back to my horizontal motion and solve for that X value here, simply, okay? All right, so let's go ahead and plug in our numbers. So V naught Y, we just solved for. Vy is our maximum height, velocity in our Y directions, that's 0, okay? So 3.78 minus 9.8 squared times T. Whoops. That kind of got crazy there. There we go. Okay, so then we solve for T. That is going to be, add that over 3.78 divided by 9.8. Okay, and that is going to be
I
approximately.
really appreciate you doing this. Thank you so much.
Yeah, no problem. I was definitely confused too, so this works out.
I took calculus, but this is not great.
It's not the same. It's definitely not the same, especially like I'm so used to calculus, and then I try to do algebra and I'm like, wait a minute, how do I do this
Oh
again?
yeah, I don't know how to add numbers. What happened?
Exactly. That's exactly my problem. Okay, so I have the time now, and as you can see, it is the same as what I solved for earlier. So I guess we could have went and kept this entire craziness over here, but God, this is so much easier. Okay, so we're gonna go ahead and go with this way.
Can I see number 4 again?
Yeah, where was that? That was down here, I believe.
I
So
love
I'm not,
your work.
oh, thanks. I'm not completely finished with number 7, but I'll go back up here in a minute.
I just want to see it.
Yeah, I can upload these if you guys want. See, I have even like the other ones from my lectures.
Yeah,
I wasn't sure if that would be,
amazing.
beneficial, but sure, no problem.
Thank you.
Mm-hmm.
I'll print them out, look at them every day, and be like, yes.
At least my work is appreciated.
I am so confused. I was like, I need help.
That's fine. That's why I pushed back the homework and everything, because I know that nobody was like asking me things, but I knew that there was confusion.
I was like, just give me a chance to ask. Once you said there was going to be a Zoom, I was like, oh,
Yep.
There we go. Okay, you can go back to.
Okay.
Wait, is that just C?
That's C right here. This was B, I believe.
Okay.
Yeah, this is part B. I didn't do A.
All right. I'm good then.
Okay. So moving back up here. So now we have our time, which is important. Now we can simply solve for that, that X value. So we're just gonna go right here and solve for that horizontal position. So x equals x naught plus vx times t. So we have our time. Our vx is also going to be v naught x. Remember, it stays the same throughout the projectile motion. Okay. I'm going to claim that my x naught equals 0 meters because they never told us otherwise. Okay. So that's what I'm going to do. So I'm going to say x is equal to 0 meters plus v naught x, which is going to be my initial velocity in the x direction, which happens to be given to us in the problem. Oops, that was kind of funky, but it's 4.5 meters per second. Because it says that he was horizontally running, not vertical running, right? Okay, and then our time is 0.39 seconds.
Wait, is this still B?
Yes,
Okay.
this is for 7B. So I got 4.5 times 0.39, and that gives me my position. Whoops, 1.76 meters. Okay, so this is the position that this guy needs to start jumping in order for his maximum height to also be the maximum, or the hoop height, I guess. Hoop height. Okay. So now 7 is done, and now it's corrected, and now it's good. See, it's easy to overcomplicate things.
We're
So
all just so confused now. We're always confused.
yeah, pretty much. We'll be okay. We'll make it through the semester together. Okay. So hopefully this has been helpful, and we'll be doing this again next week. I don't plan on doing it twice a week just because you guys are my only class. So I don't plan on doing it more than once a week. But we can always do, you know,
Wait.
yeah.
Did you number 8?
I did talk about number 8 earlier, yes.
Can I see her? I want to see her.
Well, I actually just kind of talked about it.
Oh, okay.
Yeah, so these will be posted. But yeah, I talked about the relative velocity. There's no math. I know it says calculate, but there's really no math involved.
The essay type paragraph scared me. I was like, no.
I know. I get that. I get it. But yeah, you just need to basically understand relative velocity, and then you can just look at the picture really. And then I have a little explanation about relative velocities, and I did it in this little Zoom meeting too. So once I post it, you can just listen to me. And I give you the answers by talking.
All right. Works for me.
All right, cool. All right, so we're now past by about 10 minutes, but that's okay. That was kind of my fault.
No, it's fine. It helped me. It helped me. I don't care.
All right, so hopefully this helped you guys. If you have any more questions, feel free to email. I know that this is due tonight, so hopefully all of this stuff helped. And then you can turn.
You're gonna post the notes too?
Yeah, I'll post those notes as well.
Yes. Yes. Good stuff.
All right. Well, thank you guys for coming and asking questions. I appreciate it.
Have a nice day.
Thank you. You too. You guys have a good day.
I'll try to turn it in tonight.
Sounds good. Try your best.
Bye.
All right. Bye.